container image is the immutable blueprint of an entire application. Think of it as a standardized shipping container, holding everything the software needs to run. Code, libraries, dependencies, and configuration, all sealed into a single, portable unit. What makes an image special is that it's read-only. Once built, it never changes. Every image is stamped with a cryptographic hash that identifies its exact contents, so you can trust that what you build locally is exactly what runs in production. Crack open that container, and you find the real magic. File system layers stacked on top of each other like wooden crates. Each layer captures only the changes made by a single build instruction, so no space is ever wasted. Because each layer only stores what changed, common base layers can be shared across many different images. If 10 applications all use the same Ubuntu base, that base lives on disk exactly once, saving gigabytes of space and slashing pull times. Stacking matters because of how the Union file system works. Layers are mounted in order, with the top layer providing a thin read-write surface when a container actually runs. The image beneath stays untouched, always reproducible, always identical. Bundled alongside those layers is the metadata. Environment variables, exposed ports, the default user, and the entry point command. This configuration is what tells the runtime exactly how to launch the software when the image spins up into a running container. Union file systems like OverlayFS and AUFS treat the file system as a stack of transparent layers rather than a single tree. Each layer contributes files, and the kernel presents them as one merged directory. The lower layers are read-only images, usually shared base file systems from an image like a Docker container or a Linux distribution. They never change, which keeps them lightweight and cacheable across many containers. On top of those read-only layers sits the upper directory, the only layer that accepts writes. Every change a process makes, a new file, an edited config, a deleted entry, is recorded here and nowhere else. When you list or read a path, OverlayFS performs a merged view. It searches the upper directory first, then walks each lower layer in order and overlays their contents so the user sees one unified tree. Panel B. The same sheet stacked together, and the merged root file system appears. A magnifying glass reveals every file from every layer coexisting at /, as if they always lived in one place. Copy-on-write semantics keep this fast. Editing a file from a lower layer doesn't duplicate the whole file. OverlayFS copies just the changed parts up into the writable layer, and leaves the original untouched. This layering model is why containers boot in seconds and share base images across hundreds of instances. The heavy read-only layers are reused, and each container only stores its own thin writable delta on top. So OverlayFS is the silent workhorse behind Docker images, live Linux distributions, and Snap packages, a stack of layers, one writable top, and a single merged view of the file system delivered to every process. Every Docker file instruction that modifies the file system produces a new cache layer. And 3 instructions do most of that work: copy, run, and add. Copy brings local files from your build context directly into the image. It only reads from your project directory, so it is transparent, predictable, and the default choice for shipping source code and assets into a container. Run executes a command at build time, and captures every file system change as a new layer. Perfect for installing packages like apt-get install curl, where the downloaded packages and their resulting files all become part of that committed layer. ADD looks similar to copy, but it does more. It can fetch files from remote URLs and automatically extract tar archives. That extra power is exactly what makes it dangerous. A remote URL becomes a supply chain liability, and a malicious tarball can overwrite files outside its intended path. The rule is simple. Reach for copy by default, use run to install dependencies and execute build steps, and treat ADD as a specialized tool you reach for only when you genuinely need its extraction or remote fetch behavior. Keep each layer's job narrowly defined, and your builds stay fast, your images stay small, and your supply chain stays small too. Every Docker image is built as a stack of immutable layers, each one sealed with a cryptographic hash the moment it is created. Once a layer ships to a registry, it is frozen in place. No edits, no rewrites, no takedowns. Here is the trap. When you write a secret into a layer with a run or add instruction, that secret is etched into the image's permanent history. The full command string, including your API key, becomes part of the layer's metadata forever. Many developers assume that deleting the secret in a later layer fixes the problem. It does not. A subsequent run rm command only adds a whiteout marker on top. The original layer, with the secret still intact, remains beneath it, untouched and fully readable. Anyone with full access to your image can run Docker history. No trunk can see every instruction verbatim, secrets and all. They can also Docker save the image, untar the layer, and grep through it directly. Your credential is now a public artifact. This is why layer hygiene is a supply chain audit priority. Image history is a permanent ledger, and every credential you bake into it is a credential you have leaked. To auditors, to attackers, to anyone who pulls your image. The fix is simple but non-negotiable. Never let secrets enter your build context in the first place. Use multi-stage builds, build kit secret mounts, runtime secret managers, and CI variables injected at deploy time, never at build time. Welcome to this hands-on demo. We will inspect a downloaded layer payload using only standard Linux tools, no Docker daemon required. Each command is a forensic step that validates what we are actually working with before we trust it. We start by clearing the terminal so the audit output stays easy to follow from beginning to end. A clean canvas prevents stale output from polluting the evidence chain of every subsequent step. Next we fetch the payload. The silent and follow redirect flags let curl pull the file quietly without progress noise, dropping it into a scratch location so the real working directory stays untouched. When the command returns without output, that is exactly what success looks like. Now we measure the artifact. Word count in byte mode tells us exactly how large the downloaded payload is, which is the first sanity check against what we expected to receive. A suspicious mismatch in size is often the earliest warning sign of tampering. We then bundle the payload into a compressed tarball, mimicking how container layers are packaged for transport. The C flag creates an archive, Z applies gzip compression, and F names the output file we will inspect next. Listing the archive contents confirms what is actually inside the layer. If an unexpected file slipped in during the fetch, this is where it would surface, long before the payload is promoted to production. Hashing the payload produces a unique fingerprint. Any later change to the file, intentional or accidental, will produce a completely different SHA-256 digest, which is why signed container layers always carry one. Finally, the file command inspects the bytes themselves and reports the content type. This catches the classic deception where a renamed or mislabeled file claims to be one thing, but is actually another, closing out the audit with full confidence in what we have.